Okay, Assalamualaikum and a very good afternoon. Now let's have a look on an example of a discrete time signal. So this is from the past year's test or exam. So a discrete signal as shown in figure Q3C. Okay, so from this figure, you need to write down the mathematical expression for signal xn. Alright, so the xn and representing the discrete position or discrete signal. So you need to revise back if you have only one point. This is known as unit impulse and the equation is del the n position. Alright, and depending on its position here, it's beginning from 0 up to n. So again, you need to consider the shifting position. Alright, so here in n minus 1. Why n minus 1? Because shifting position rules is n minus n naught. So n minus, in this case positive, n naught. Okay, you have positive n naught on the right hand side. Right, if you have only one unit impulse, so it is represented by delta function. But if you have a series of impulses, all right, with the same magnitude, 1 up to infinity, and n domain, so this is called the unit impulse function, un, okay, or unit step function for n domain. All right, so if you have only single at certain position, you should represent it with delta function. All right, so in this case, so let's look at the signal you have. So it's basically you have multiple impulses at different positions, so you need to consider writing your equation in delta n function. Right, so let's look at the first. So the max is 2. So as long as it's quite simple, as long as you can identify the position, so you can write the equation straight away. So in this case, your xn, so you have start from the left hand side. So you have the magnitude of 0 at n equal to minus 2, and then so you don't have to write it because the magnitude is 0. So at the one that have amplitude is here, its magnitude is minus 2, and then delta and minus 1. Okay, because it's at the position of n equal to minus 1, and then plus the magnitude of 4, and again delta function for n minus n naught is 0 in this case. Right, next you have a negative 4, and then delta, and its position is n minus positive 1, and then you have 0 here, magnitude, and also here, so you have another one here, it's positive 4 delta and minus positive 3, and then finalize your equation. So your xn is equal to minus 2 delta n plus 1 minus plus 4 delta n minus 4 delta n minus 1, and then plus 4 delta n minus 3. So this is your equation for signal xn. So you can get 2 marks out of this equation. Okay, the final question in the example is question 3b. Don't forget to write down the question number 3b. Right, so sketch fn. Okay, given xn, so you need to sketch a new signal given by fn equal to negative 2x 0.5 n minus 1. So meaning that something happened to the original signal Sn by using this function so that it will produce fn. So again, if you have signal operation, you need to use, or you may use method 3 in order to sketch a signal. Okay, so let's begin with the first step. You need to identify the component inside the bracket and then represent that as tau. So Fn equal to negative 2 x 0.5 n minus 1. So let's look at the what happened to the signal. You have scaling, and then you have shifting, and then you have amplitude inversion and also amplitude scaling. Okay, so you need I'll recommend you to solve the time-based operation first inside the bracket. So now represent the one inside the bracket as tau. So tau equal to 0.5 n minus 1. So what is your new n? New n equal to tau plus 1 divided by 0.5. Okay, so also equal to 2 tau plus 1. So what is your tau? Tau is basically the value of n that being converted into tau. Okay, so let's draw that signal again. So now the axis n becomes tau, right? So it's 0, negative 2, negative 1, 0, 1, 2, 3, and 4. And in a discrete signal, it's very important to arrange your signal sequentially, okay, to so that the end position is aligned to the next graph, because it will be easy to multiply or to add or to subtract them, because all operations you need to do considering the same end value. Okay, if it is at 1, so the subtraction must be done at 1 as well. Right, so for the given signal, at 2 is 0, and then at 1 it's minus 2, and then it's 4 at 0, and then it's minus 4. It's minus 4 at 1, and then 0 again, and then positive 4 again, and 0 again. Right, so change the n to tau. So now consider the tau values into to determine the new end position. Okay, so when tau equal to, although the magnitude is 0, so you still need to consider, because based on the calculation, you may have magnitude in the new end axis. Right, so when tau equal to minus 2, so your new n equal to 2 plus 1, 3, 6. Right, so tau next is tau equal to minus 1. It's n equal to 2 minus 1 plus 1 equal to 0. When tau equal to 1, n equal to 2, 1 plus 1 is 2, 2, 4. Is this correct? Ah, sorry, it's minus 2. Minus 2 plus 1 is minus 1, minus 1, minus 2. It's minus 2 here. Alright, so tau equal to positive 2, and then it's 2, 2 plus 1, 3, 2, 6. Tau equal to 3, n equal to 2, 3 plus 1, 3, 1, 4, 8. And then tau equal to 4. It is n equal to 2, 4 plus 1, so 5, 10. Right? So now you already have your new end axis values. Alright, so now use the new end axis. So when tau equal to minus 2, it becomes minus 2. When tau equal to minus 1 is 0. When tau equal to 0 is 4. When tau equal to 1, it is 4. Sorry, minus 1. Is this? Am I doing it right? Let me consider again. So tau equal to 0. So n equal to 2, 0 plus 1. Okay. so it's 2. Okay, here it's 2. Okay, minus 2 and then 0 and then 2. When it is 1, it is 4. Okay, look at this. I try to align them accordingly in the same arrangement. When 2, it is 6, and it is 3, 8, and 4 is 10. Okay, again, redraw the same magnitude on the new end axis. So it's 0 here, and then here it's minus 2, and then you have 4 here, and then you have minus 4, and then you have 0, and you have 4 here again, and then here. Okay, so now this is the function for the one in the bracket, fn equal to 0.5, x, so I should use bigger space. Okay, so this is the function for fn equal to x 0.5 and minus 1. You haven't done the amplitude part, sorry, negative 2 part, right? So in order to get the fn equal to minus 2x 0.5n minus 1, so you need to multiply the amplitude with minus 2. So all this amplitude need to be multiplied by minus 2. Alright, so you need, meaning that the amplitude will be inverse and the magnitude will be scaled up by 2. Right, so in this case, the same position, and the arrangement is okay. You start with negative values up to the maximum positive values, so you can just simply copy the position, negative 2, and then 0, 2, 4, 6, 8, and 10. Okay, right, so okay, let's consider the first one. The magnitude is 0, so multiply with negative 2 is still 0. And then the second one at n equal to 0, so the magnitude is negative 2, multiply with negative 2 is positive 4. And at 2, it is 4, multiply with negative 2 is negative 8. Right, at 4 it's negative 4, multiply with negative 2 is positive 8. Okay, please draw this accordingly, but due to this limitation, so I just put the magnitude as 8 here. Okay, at 6 is 0, and at 10 also 0, and then at 8 is 4, multiply with negative 2 is negative 8. Okay, so this is the final answer for f for the given function f equal to negative 2x multiplied with 0.5n minus 1. Okay, so this is the y-axis. So this is your final answer in order to get the full 3 marks. Okay, with that, thank you.